Hello, it's Keith here, and this is lesson 5 of the platform-specific series of my 6809 assembly programming tutorials. We're going to be looking at the Fujitsu FM7, and I think I've got something quite special today. We're going to be looking at the graphics on this system, but the graphics on this system are really quite unlike pretty much any other system because it's actually got two 6809 processors, and for most graphical commands what we do is we send a sequence of commands to the second processor, and the second processor does what we want. Very much like the MSX2, I suppose, in a lot of ways. The only difference is that we can actually program the second 6809 as well via some dirty tricks. So this is going to be quite a long video, so if you're one of these people who tends to give up on my videos halfway through, you might as well just go away now and go watch cat videos or whatever nonsense you prefer to do, because as I say, it's going to be a long video. It's going to get in depth because that's what we do around here. Okay, so let's make a start. So we've got the title here, 2 CPUs are more annoying than 1, because unfortunately the problem is that the second CPU doesn't really speed things up very much. The second CPU is another 2 MHz 6809, so it's not faster than the first one, and the second one, while it can be drawing away while the first one's thinking, if we're wanting to send a lot of commands to the second CPU, we're going to be waiting for the second CPU to finish its first command before we can send the next one. So often it's not that much faster, but anyway, that's how we have to access the video memory. The main CPU, the CPU running our commands, can't access the video memory directly, so we've got to deal with this second CPU in some way. Now, how do we tell that second CPU what we want to do? Well, there's a shared area of 128 bytes. On the main CPU, this is at memory address FC80 to FCFF. It's a different address on the sub-CPU because we can access and program the sub-CPU. It's at D380 to D3FF on the sub-CPU. So those are effectively the same memory area. Now, I think what actually happens is I think maybe the ROM copies it, or maybe there's a DMA copy. But as far as the system's concerned, they are both the same area of memory. Now, the other thing you need to remember is both CPUs cannot access that memory at the same time. So if you are writing some data to the sub-CPU, you need to stop the sub-CPU, and then once you're finished, you restart the sub-CPU and it will start processing that data. If you need to check the response, you need to halt the sub-CPU again, read the memory back, and then you also, and this is the tricky bit that caught me out, you need to make sure that that memory now has something that when the sub-CPU looks at, it's not going to mistake it for some crazy command and crash itself, because it can apparently do that. So that's another thing we're going to be dealing with. So as I say, it's an in-depth lesson, a lot of content, but this is what the FM7 requires for us to do to get things working. So we're going to have to learn how to check if the sub-CPU is busy, stop the sub-CPU and start the sub-CPU. And actually this is all done with basically just 1 or 2 bits. Well, let's go over to our source code and let's see a typical command. So here we've got our example for all of the graphics examples today. We've got a variety, not all of them, there were a heck of a lot. This is effectively, I think, the most useful ones. There were some character commands and things that I'm just not covering. We've got some commands to do things for us simply to send data to the CPU automatically, but we're going to of course look at how those commands work as well and go into the sort of real details of what needs to happen. So our procedure for sending data to the sub-CPU is stop the sub-CPU, transfer the data to the shared memory, and then release the sub-CPU. And the action of releasing the sub-CPU will mean the sub-CPU will now process the data that we've put in the shared area. How do we halt the sub-CPU? Right, well, first of all, we're going to have to check if the sub-CPU is still working on something, because we want to let it finish what it's working on. Now, if we want to check if the sub-CPU is busy, we check the top bit of port FD05. Now, the top bit, bit 7, can be tested by checking if the register A is positive or negative, because remember the top bit being 1 means it's negative. So here we're just testing if the top bit is 1, and we're looping so long as it is 1, and then we're returning. So running this wait command will pause the main CPU until the sub-CPU is ready to actually start doing something. We've got effectively the same command here, just rather than jumping here and wasting some memory and speed, we've got it built into the halt command. So we're just waiting here until the CPU is no longer busy, and then we're writing the top bit to 1 to that same port FD05. Reading it and getting a bit 1 means it's busy. Writing a bit 1 means that we want to halt the sub-CPU. And that's what we do. And then we are just waiting for the halt to actually happen here. And once the halt has occurred, we can then carry on with our processing. So we're effectively doing that just here, and then we're transferring the data to the sub CPU. And the transfer command is very straightforward. Here we're just transferring words from our source, whatever the source is, that's going to be a set of bytes, to the destination, which is memory address FC80 or FC82. Why FC80? Well, because that's obviously the shared air memory. We're often only writing to FC82, however, because a lot of these commands don't actually care what the first 2 bytes are. Some do, but the vast majority simply don't care. So to save 2 bytes of transfer and memory, we're just skipping them over and we're transferring from FC82 onwards. Okay. Now, what do we actually need to transfer? Well, that varies entirely depending on our command. So here's our clear screen command. This is the first command we're going to be looking at. Okay, and what do we do? Well, we're going to load in the address of this test CLS definition here, and we're going to transfer this to memory address FC82 in the shared memory. Now, because we're transferring words, we're dividing by 2 here, so this is the length divided by 2 because we're transferring words, and we're running that subcpu do command that we just saw. And as I said before, that is effectively going to halt the subcpu. It's then going to send that data to the shared RAM at FC82, and then it's going to resume the subcpu, which is going to process the command. What's the command we're transferring? Well, it's effectively a clear screen. This is command hexadecimal 02, and this takes 2 bytes. Now, the first one I don't think is very useful. It's something to do with paging, but I don't think it actually has any real effect in most cases. The second byte, however, it does have a good effect, and that's the color. And the color we're using is color 1, which is blue here by default. These are all changeable, the colors. The colors are all highly configurable, but they're always the very prime colors. You can't have nice subtle shades, unfortunately. So here's our clear screen, and you can see we've cleared the screen to blue. If I just change this, if I change this to a 0, well, now we've cleared the screen to black. And if I change it to a 6, well, guess what color? Well, we've changed it to yellow here. So we can change to any color we want here. So you can see we've now got a yellow, and you're possibly getting some nasty interlacing effects from the emulator here. Anyway, you can see here that this command 02 will transfer a yellow byte here. Now, this is transferring to memory address FC82 because the first 2 bytes at FC80 and FC81 do not matter. It doesn't matter what's there. So rather than waste an extra 2 bytes here, it just didn't make sense to do that. So we're just skipping over those 2 bytes there. So that's our first clear command. And you can see, despite all the pain of messing with the subcpu, the actual command is very straightforward. And if you're using my sample code here, hopefully you can get it going pretty quickly. So that's the clear screen command. Now we're going to try some plotting of points. You can see if you're not looking on a mobile phone, but you can probably see there's 2 dots there. Can we make this any bigger? Maybe we can't. I don't think we can. How disappointing. Anyway, you can see there's 2 tiny little dots there, and that's this points command. So here's the definition for our points command here. You can see again we're loading to FC82 here. This is basically exactly the same as here, only the pointer, instead of pointing to test CLS, we're now doing to test points. The points command is number hexadecimal 17, and the byte immediately following is the count of the number of points. And in this case, we've done 2 points here, you can see them, and we define an X position, a Y position, there's a 16-bit, a color, and then a logical operation. What logical operations do we have? Well, we've got things like pset, preset, which I believe sets back to the background color, or, and, XOR, and not. Now, I think, really speaking, you're probably going to just want to use pset or XOR. XOR will, of course, invert things. That's quite handy if you want to do simple sprites, because you can remove a sprite from the screen and leave the background intact if you do an XOR over the top of the original sprite. So that can be handy. But I think the others possibly not so useful. But anyway, we're going to see them a bit later on a command that's a bit easier to visually see what's going on than the points command. Here you can see we're doing 2 dots, but we can change this. If we just change this to 4 here, and we just copy this, and we'll put another 2 dots here, and we'll put one at 161.111 and 162.112, and we'll change these to colors 5 and to colors 4. If I can learn how to type properly, possibly I can't. Okay, and now you can see here, even though I can't see what colors those are, they're too small. Anyway, they are definitely different colours. I can see one's green and maybe the other's probably cyan, but as I say, they're a bit small. But anyway, we can plot points to the screen. Very good. Now, of course, the number of points is just defined by that just there. So that's points. Next, we're going to look at the put command, and the put command is a little bit misleading because I think in QBasic put was draw a sprite. In this case, unfortunately, it's just drawing text. Now, this is actually sort of going through a kind of terminal emulation, so we have some commands that aren't just relating to printing text. I don't believe we can change colors in this way, but we can locate new locations on the screen and move the cursor around. And so what I've done here is I'm using command hexadecimal 12, and that's locate, and I'm specifying an X and Y position of 5,5, and we're printing hello here. Now, the command in question does actually use the first 2 bytes. So instead of writing to FC82, which the vast majority of commands will do, this will do FC80 onwards. Now the first byte is the continue command. In this case, we're not continuing, we're starting a brand new string, so we put a 0 there. But if we wanted to put more strings at the end of the last one, we would put a 128 there. But in this case, we're not doing that. Now we're specifying command 3, put. We're specifying the byte count, and we're specifying 5 for our 5 characters here, and then 3 for these 3 characters here, because the locate command itself is characters. So if we just run this, we can see hello, and that's at 5,5. If I change this to 15, well, you can see it's now much further along the screen. So anyway, hopefully you can see that we can actually get text onto the screen with some movement possible there with that put command. Now we're going to look at something a bit more advanced, the symbol command. Totally misleading titles here, nothing to do with symbols really. This is more the graphical text option. So again, we're this time writing to FC82 again, so those first 2 bytes when used. Command 19, we can specify a color number, a function, so pset, XOR, all of that kind of thing. Again, I covered them up here. The 0 is pset, 4 is XOR, and so on. We'll see those when it comes to boxes, I think, because that's a nice easy way of seeing what the XOR does at least. So there we go. So we're specifying pset here. We can specify a rotation in 90-degree increments. 0 is normal, then notated 90, 180, 270, and we're rotating to 270 here. A scale, we're scaling twice X and Y, an X and Y position, and then a count of characters. And we're printing FM7 rocks, which I think it's very nice, possibly a bit over enthusiastic there. I think the speed is slightly disappointing because of the graphical methods, but you can see here we've got this rather nice text here, FM7 rocks, and we can change the scale if we want. If we just change this to a 6, and if we just change the color to a 4, well, now we've got taller text and it's in green, but you could see it drawing there, and as I say, this is the problem, that we don't really have hardware acceleration, we just have second CPU acceleration. So it's interesting, but unfortunately, from what I've seen of the FM7 games, they don't really have the speed of the Amstrad CPC, which does not have a subprocessor. So I don't really think it helped, unfortunately. Anyway, though, it's a lot of fun to play with. So there we go. So that's how we can draw some nice snazzy graphics on the screen, some text graphics. Next, what we're going to do is we're going to draw some lines. Now, lines are lines and more. We can draw lines and we can draw boxes, and we've got a few different versions of this command here. So we've got test line, test box, and test box 2, and again we're transferring to memory address FC82 here. Now the command is the same in each case, hexadecimal 15. It's the fill mode. Fill mode 0 means draw a line, fill mode 2 means draw a filled box, and fill mode 1 means draw an empty box, a square effectively. So if I just fire this up here, we'll see what boxes we've drawn to the screen here. Now, first of all, we've drawn this line here. This line has been drawn in colors 2 here, and it's fill mode 0, so that's just a straight line. And then we've drawn 2 boxes here with color 4, which is green, and with logical operation 4, which is XOR. And that means that when the second box overlaps the first box, the part in between has been XORed. If you think of the logical operation with regards to your hexadecimal and your assembly language, you'll know how that affects the bits, and that has caused that to be inverted. Now the result will of course depend on the bits we select. So if we select color 5 here and run this again, well, now the inverted area is neither green, nor cyan, nor black. It's actually blue, and that's again because of the way it's working at the bit level, so the bits have been XOR'd there. Now this red line here, we could change that to an empty box by changing this bit here. If we change this, we've now drawn an empty box. So these line commands have a lot of flexibility, and calling it line is really really understating the command. It's got a lot more things that it can do other than just lines. Okay. Now we're going to get even more creative with the fill command. Now fill is very surprising in a lot of ways, because this is something that even Amstrad Basic didn't have. So it's impressive to see. Once again though, I think it does show the limitations of the FM7, where you can see how slowly that was filling, and of course that's a second processor working in assembly language. It's not just some basic command running it. So it's certainly okay if you were trying to do your Gremlin style text adventure. It's probably going to be enough for you, but you're not going to be drawing you're not going to be doing the next Total Eclipse Castle Master type game using this fill command. I think you can say that much. Anyway, in this example here, we've used the box command that we just saw. We've drawn a line, we've drawn an empty box here, and then we've filled that box with a second color here. Now you can see here that the outline is green and the fill here is white. Now the way this command works is a little bit interesting. We have to specify the boundaries that we will stop at. So we've specified 7 boundary colors, and colors 1 to 7 here, effectively meaning we're just going to fill black. Now if I change this, and if I remove color 4 here and I change this to 6 boundaries, well, we're going to have quite a bad day, because now it's going to ignore the green boundary and it's going to fill the entire screen. Whoops. Well, anyway, that was exactly what I intended to do, because I wanted to show you that the fill command could be set to ignore certain boundary colors. I mean, that'd be handy if you wanted to maybe erase some bits of text that were inside the box and just clear the entire box. Maybe you had a cyan boundary and some green text in the middle, and you just wanted to black out that text quickly. Maybe you could do that. But to be honest, if you were doing that, you would probably just want to use a filled box anyway. So I'm sure there's some use for it, but I can't immediately think about it. Anyway, it's hexadecimal option 18 here. We just specify the XY position, the color, and then the number of boundary colors there. So yeah, it's an interesting command, just a little bit slow, unfortunately. Another very interesting command is the change command. This allows us to swap colors. This time we specify a range, a start and an end position. This is code hexadecimal 1A. We again write to FC82. It doesn't use the first 2 bytes, like most commands don't. And then we just specify the old and new colors. In this case, we've got 2 swaps we're doing. We're swapping color 7 for color 6 and color 4 for color 3. Let's just fire this up. Now, I was just slightly hoisted by my own petard there. This test actually uses the fill command, and because I'd messed with the fill command, it was messing this test up. So now I've fixed that. Hopefully we can see what it's supposed to do. There we go. It's done that original fill. And then this yellow area here is the color swapped area thanks to this change command. Now, yellow is of course color 6, and so we've swapped color 7 for color 6 here. Color 4 is green, and of course our boundary, if you can see, is green here, and that's being swapped for color 3, which is magenta, and you can just about see that here. So you can say anyway, we can actually swap colors, and so maybe if we swap these around, maybe it'll be a little bit clearer. So let's try swapping this for 3 and this for 6 this time. And this time you can see, there we go. So we've swapped the white for magenta this time and the green for yellow here. Possibly no clearer after all. But anyway, again, it's a very clever command. I can't immediately think of a case where I would particularly want to use it, except for making a simple graphics package, I guess. But as I say, it's a clever thing to have. So that's another option for us. Now we're going to now look at reading in the keyboard. Now we did look at reading in the keyboard last time straight from the hardware registers, but if for some reason that's not good enough for us, we can actually get the second CPU to do that for us with command hexadecimal 29 here. Now this one we are writing to memory address FC82, but when we read back, we need to read back from memory address FC83 and FC84. If I just fire this up here, now we've got nothing happening here, and that's because it's waiting for us. If I now press A, you can see we've got a value returned of 61, and that is character A. If I just run it again and I press space, we will get hexadecimal 20, and that's the character for space. And the 1 here in the second byte represents that a character was successfully received. Now, what are our options here? Well, firstly, hexadecimal 29 is the in-key command, and then we have an option here. We can either specify to wait, and we can specify to reset the buffer. We could alternatively just read in a character that was waiting in the buffer, you see. But in this case, we're setting it to wait. Now, unfortunately, it's a little bit tricky. This took me a long time to get working because the send command is exactly the same as before. But when we want to read back the result, we need to read back that shared memory. So we need to halt the subcpu again so that we can read back that shared memory. And we read in FC83 for the character code and FC84 for the true false of whether a character was read. Now that's all very well and good, but when we release the CPU, the sub-CPU, it will start executing whatever is in memory, and what will be in memory is some random codes as a result of our commands here. And the problem with that is that it confuses the sub-CPU. So what we need to do is we need to put something in there that the sub-CPU will understand, and something that we'll cover later that the sub-CPU definitely knows to understand and it knows not to do anything with is the command 3F followed by 00. Now 3F is a special command which we'll cover later on, and 00 will tell the sub-CPU, well, just give up processing this command. So that's kind of an easy, safe command to send to the sub-CPU that it will ignore. So when we release the sub-CPU, everything carries on as normal. If we'd crashed the sub-CPU, our monitor command wouldn't show any text. And I can just prove that to you if I disable these and I run again. And now I press A. Well, I'm pressing keys and nothing's happening. So yeah, we've got to kind of negotiate with the sub-CPU there. Anyway, that's how we can read in a key, but to be honest, I would use the example I showed you last time on how to read in from the port directly and how to use an interrupt handler. Now, we're going to get to the good stuff now. We're going to look at the put block command. Now, this is effectively the send sprite command. Okay, so we've got a sprite. Well, we've got one lurking around somewhere. Where is it? Here it is. Here's our bitmap test FM7, and it's Chibico as always. So I've exported in the correct format. AccuSprite Editor outputs in every format for my tutorials. So this save raw bitmap option on FM7 here will output in the format for today's example. So that's what we've done. We've got that file there, and we're going to send it to the sub-CPU. Now, the sub-CPU memory, if you remember, is just 128 bytes. Now, this image is 48 by 48, which is a lot more than 128 bytes. So what do? Well, we split it up into multiple blocks, and we send each one as a 128 byte block, and we tell the sub-CPU to process it. The sub-CPU can understand how to do this. You see, this is one of those commands that uses FC80 onwards, the full range, and we can specify a multi-block command with command 128 at FC81, and we use 1E the first time, which is put block 2 command, which is the bitmap command effectively, and then the second time we use 64, which means continue, and then we specify the number of bytes, and I'm sending 96 bytes each time. And so I'm sending my bitmap file in 96 byte chunks here. Let's just fire this up and let's see what happens. Well, there we go, we've got a Chibico there. So that looks quite nice. And if you saw very quickly, you might have seen the bit planes kind of build up there. But that's created the Chibico character on screen. It looks very good, and it wasn't too slow. It wasn't amazingly fast. And again, I think this is one of the big problems with the FM7 and its speed. So we've had to basically break up our bitmap, but this code has done that for us. It's just transferred 48 words each time of our character into the command, basically tagging them onto the end of the commands here and putting them into that 128 byte block. So that's how we've been able to get our Chibico character onto the screen in this case. Now, as you say, that is a little bit slow, and you're probably thinking, well, can I create a game that draws graphics with that speed? And the answer you're probably going to come to is probably no. And that fortunately is a trick. Now, you remember I said that 3F command would be ignored if we followed it with 00. Well, the 3F command is known as the yamauchi command. This is a secret command which was undocumented in the FM7 documentation, but it was basically giving the programmer the ability to transfer code straight to the sub-CPU and execute it on the sub-CPU, giving the programmer the ability to do whatever the flipping heck they wanted with all of that video memory. So at this point we need to actually understand the video memory, and here it is. So this is a sub-CPU, and the video memory on the FM7 is very straightforward. 0 to 3 FFF is the blue bank, 4000 to 7 FFF is the red bank, 8000 to B FFF is the green bank. We've then got some buffer area, which I think we can do whatever we want with, because I don't think we need it if we're not using the console. And then we've got some work RAM here, which again, if we're being really malicious, which I think we would have to be if we were doing games, we would probably want to wipe all of this out and actually put our own program code in these areas and sprites and do nothing with the commands we've just discussed and do everything with the Yamauchi commands. So that's our sort of work area. That's our video area, and there is a trick that we can actually disable one of these banks and use a 4-color screen mode. We'll discuss that in a moment. This area unfortunately is I/O and ROM, so don't get clever ideas that you're going to use this area. Basically this is the only area, maybe this much, that you can use for graphics, and this is the screen, and probably if you're in 8-color mode this is the screen. So anyway, as I say, that's how we work. Now, as I say before, when we transfer data from this area in our main CPU, it ends up in this area in our sub-CPU. So any data we're going to have to transfer is either going to have to understand that it's going to be running at the D380 range, or it's going to be relocatable code that it won't matter where it ends up running. Now, that's the memory of the sub-CPU. How do we transfer the command? Well, 3F is the Yamauchi command, and the sub-CPU, when it sees a 3F, will look at the following bytes, and if they're not Yamauchi, it will ignore them, which is why we were using 3F00 as a dummy command earlier. But if we do specify Yamauchi, then what follows next is one of 3 commands. Now, it's actually a 4th one, but it's not very useful. 90 is an end of sequence. 91 is a transfer data command. 93 is a jump to subroutine command, after which execution will continue with processing the ROM. And 92 is actually a jump command. That's not so useful because that would kind of lock your CPU up, and why not just use jump to subroutine? But anyway, so what we're doing here is we've got a command here. We're going to basically transfer this entire block, and this block contains a sequence of a Yamauchi initialization command here, a transfer to memory address C000 command here, and then an execute memory address C000 command here. And what we're transferring to C000 is actually this little program here that is also in the same 128-byte block. A little bit confusing, I know, but I thought this was hopefully enough for a simple example. This is simple-ish, I guess. So this is going to be transferred to C000 by these commands. You can see we're specifying the source address here, which we're calculating as an offset from the shared memory. And then you've got the destination here, and then you've got the length here. And so we're transferring this program to that C000 range, and then this program command 93 will run it at C000. So this will actually run at C000. Now, I know technically speaking we could have just run it from the shared memory area, but I thought transferring it to C000 was a bit more snazzy, and it does mean we could run it later on if we wished with a separate execute command. We've got one somewhere, I think. Yeah, if we wanted to execute it a second time, we could just use this shorter command here, which is just a 93 followed by a 90. The 90, of course, is just the end of sequence command. So we can actually run it again later, and that is why we might want to transfer it to the common area rather than running it straight from the shared area. Well, what does this command do? Well, it's just a basic sequential copy. It's copying from memory address 4001 to memory address 4000, and it's repeating until it gets to 8000. Well, what does that do? Well, the 4000 to 8000 range is the red video memory. So we're effectively shifting the entire red video memory 1 byte to the left. Now, if we just go over here and we just execute this, well, the entire red video memory has shifted 1 byte to the left, and it's given this kind of splitting. And if I get my old 3D glasses on here, I can now actually see that the screen looks like it's inset in 3D. So there might be cases where we actually want to do weird shifts to the channels like this, but really it was just a simple test to show that we could directly manipulate the video memory. And if you think how long it took to draw that sprite before, well, now that's very fast, and that was the entire screen. It wasn't just the visual area here. So by using the Yamauchi commands and by directly accessing the video memory and using areas of the video memory for sprites and areas of the video memory for visible screen, we can hopefully get some faster commands that are actually going to give us a vague chance of making a game with some speed to it. That's the hope anyway. So that's what the yamauchi command does. And as I said before, it was totally undocumented. You know, they always complain about Microsoft keeping secrets to themselves so they can write faster code, and I'm sure they did. But FM7 were being pretty sneaky keeping that secret. So anyway, fortunately we know about it now. Now, as I said before though, unfortunately there's very little memory by default accessible to us, and really just probably this area, because all of this is used by video memory, but there is a way we can get around that, and we can cut down from using 3-bit planes to just 2, and we don't have to sacrifice any colors. Unlike systems like the Sinclair QL with its 8-color palette, the FM7 does have options where we can reconfigure how the bit planes define colors. Now, what we're going to do here is we're going to define each of the colors and we're going to swap them around. Now, colors 0 to 7 are defined by memory addresses FD38 to FD3F, and each of these takes a single byte. There's just 1 bit per channel, and it defines the combination of channels that make up that color. So, for example, white would be 111, black would be 000, and magenta would be 011 in this case. So it's green, red, blue format. Now, what we're going to do here is we're just going to prove this by sequentially transferring the colors of white and then magenta to each of the colors from 7 to 0 onwards with a delay in between. And this will show us each color. You can see here that the colors from 7 to 0 are changing white, and now 7 to 0 are changing magenta. There we go, so they all change. So really we have a total control over what colors we have on screen and what bit planes end up being what colors, and this gives us some more flexibility. And it also means we don't need to use all of the bit planes for visible memory. We can actually basically hide a few of them. Now in this case we're hiding them just by making them the same color, but we can actually even completely turn them technically off. So we're going to have a look at that now. So that's how we can select how the bit planes appear as visible colors. But if we look at the masks option, this gives us some really quite clever, interesting functions. Now, I've not really seen a system before that allows us to turn off bit planes, but the FM7 goes even a step further than just turning them off. It actually allows you to show them, but not write to them. So we have 2 options here. This is port FD37. And the bottom 3 bits are write bit planes, and these will disable one of the bit planes from being written to. Now they're marked as green, red and blue, but this would only be using the default palette. If we used a custom palette, these could now be completely different. Green could now be red and blue could be green, and it just depends on the color configuration we've used with these settings here. But these are the defaults, and so by putting a 1 here, we're disabling the display of a bit plane. And by putting a 1 here, we're disabling the write of a bit plane. Now, what's the difference? Well, if we're writing to the screen, but we're not displaying it, then the colors will look different. But when we disable the display mask, then we will see all the colors had actually been written. Whereas if we disable the writing, we will still be able to see all of the colors, but some of the bit planes will be being ignored as the writes occurred. Well, let me show you what I mean here. So here, first of all, we're changing the display bit plane here. If I just press a key here. So first of all, we showed the monitor as normal. Now we've disabled the green bit plane, so we're just seeing red and blue, which means that the white now looks magenta. But we're writing another monitor, and now we've disabled another bit plane, so now we can just see the blue bit plane, but we've still enabled all of the write masks, so all of the writing is still occurring as white. If I press again, now we've just disabled the blue bit plane, and because everything's actually being written as white, filling all the bit planes, the visible displayed bit planes are affecting the entire color, the color of all of these drawn objects here. So they all look yellow. Now if I press space again, this time we've disabled all of the masks for the displayed bit planes, so all the bit planes are being shown. So all of those writes here, you can see, were actually still occurring as white because the write bit masks were all disabled. It was only the display bit masks. Now the display bit masks are all enabled, and it's the write bit masks being disabled. So the red mask is enabled, and that's disabled the writing to the red channel, so we've got a cyan here. And then we've masked off the green channel, so we've got a magenta. And then we've masked off the green and red, so we've written blue. and then we've masked off the red and blue, so we've written green. So you can see here that we can actually disable the visibility and also the write to some of these bit planes as we wish, and we can really be very flexible with this. Now what I'm really sort of suggesting is we could actually disable one of these bit planes, like we could disable the entire green bit plane, giving us a 4-color screen. We could then select the palette for the remaining 2-bit planes, and then we could use all of the memory from 8000 to BFF for our sprites, and that will give us a nice bank of sprites that we could then transfer to video memory using the yamauchi commands. We could write our own sprite routine within the sub memory, probably within this C to CFF memory. We could write some pixel shift routines for sprites, for scrolling the screen, things like that. Do everything with the yamauchi commands. I think really that's your only option for a fast game. And from what I've seen, I'm afraid there were precious few of them on the FM7, which is a shame. Really is a shame, because there's a lot I like about this system. As I say, those masking options seem really impressive, but it's slow. It's so slow, which is really sad. But anyway, that's all we're going to be covering today. And well done if you've got through to it this far and you've not given up and gone and watched cat videos. I salute you. Hopefully I'm going to be able to come back to the FM7 with more graphics later on. Now there was another system after the FM7 known as the FM77 and later the FM77 AV40. They decided 8 colours wasn't enough. They went to 4096, and then they decided that wasn't enough and they went to 18-bit because, I don't know, reasons, because they could and they didn't think whether they should, I guess. Who knows? Anyway, they did it and we're going to try and use it. But that depends if I can get the manuals that explain how it works, because I've got some stuff working, but it's a bit sketchy. But hopefully, fingers crossed, we'll be able to come back to the FM7 and really show off those extra colours. So if you like what you saw today, please like and subscribe. You know, if you like the videos, YouTube recommends them more, and that means more people can see them and hopefully they'll get some benefit from them. And if you subscribe, then that encourages me to spend my money buying books on FM77s and trying to program the weird 4096 colour mode that seems to be totally undocumented in English. So if you want to see that kind of thing, you know, please subscribe to my channel. Anyway, whatever you do, I hope you're going to go and download this sample code from my website and have a go with it yourself, and maybe you'll have some fun with the FM7. But if you don't, wish you all the best with your 6809 programming. Thanks for watching today, and goodbye.